Welcome back, dear learners. This is the last module on logic-based testing of week 6. As I told you, we extracted predicates from code from other constraints like requirements, finite state machines, and wrote our test requirements, predicate coverage, ACC, whatever we want. Now we have to get test cases. For small programs, as we do in the class, we could get test cases by looking at the predicate and looking at the type of the variable and solving it. But in general, predicate could have function calls, predicates could have complex variables, and you might want some help with automatically solving the predicate and giving you values that will make the predicate true and false, or a particular resulting predicate for active clause coverage criteria, true and false, and so on. So is there an automatic way of doing it? Those kinds of tools are what we call SMT solvers. This module is an overview of SMT solvers, a very brief introduction, because the purpose of this course is not to teach you the theory of these solvers, but if needed, to tell you that these exist as tools for you to use to automatically get test cases if you get your logical predicate. So as I told you several times, the fragment of logic that we consider for testing is what we call predicate logic. So the basic entities are predicates, and predicates could involve variables of various types, integers, strings, floating point numbers, arrays, and so on. It could involve functions, function calls, addition, subtraction, an arbitrary function f of x, another one function calling another function, checking if a queue is empty could be a function, several different functions. Predicates also involve relational operators, which are less than, greater than, less than or equal to, and in going on it could have complex relational operators like set membership and so on. So typically in the theory of logic, predicate logic or first order logic also has quantifiers for all, and there exists. But as I told you right in the first lecture on logic, we don't consider quantifiers as far as testing is concerned. So just a brief recap on what propositional logic is and what are the solvers for propositional logic. So if we ignore variables of various types, functions and relations, but consider only variables of type Boolean, which we call as atomic proposition. That is, they always evaluate to true or they always evaluate to false. They are Boolean propositions. Propositional logic deals with combining these atomic propositions using our usual logical connectives. We've seen all these logical connectives. By now we are comfortable with them. Or, and, negation, implication, if and only if, and so on. You can form several kinds of complicated statements. At any point in time, as far as testing is concerned, whatever logical predicate that is, you are interested in one set of truth values that make the predicate true, one set of truth values to its clauses that make the predicate false. So that is what we call as the satisfiability problem. So satisfiability problem, abbreviated as SAT, pick up the first three letters from the satisfiability problem, that's the abbreviation, SAT, is the Boolean satisfiability problem or the propositional logic satisfiability problem. That is, given a propositional logic formula, can I give a set of true-false values to its constituent atomic propositions that make the formula true, or sometimes I might want to understand whether it also makes the formula false, like when we do predicate coverage. So we want to know if there is an assignment of true-false values that makes the given a propositional logic formula true. If it makes it true, then we say that such an assignment of true-false values is a satisfying assignment. So a satisfying assignment is an assignment of true-false values to the atomic proposition such that the entire formula evaluates to true. So for example, suppose you take a formula A and not B, as you see here. It has two clauses or two atomic propositions, A and then B. B has a negation outside it, and then they are combined using the logical connective AND. When is this formula satisfiable? If I can find one truth assignment to A and another truth assignment to be, that is true or false assignment to be, such that using the semantics of these Boolean operators, the whole formula evaluates to true. Then we say that this formula is satisfiable. In this case, suppose I assign A to be true and B to be false, which will make not B to be true. So A is true combined with an AND operator with not B, which is also true, will result in the formula A and not B becoming true. So this is a satisfying assignment. A being true, B being false is a satisfying assignment, and the formula A and not B is satisfiable. So we would want an algorithm that, given an input as a formula, checks if a formula is satisfiable or not, outputs yes or no. And moving on, we would also want the precise satisfying assignments. Like we said, assign A to true, assign B to false. This assignment will make this formula true, hence it is satisfiable. We want an algorithm to do this. Unfortunately, the algorithms that are available are expensive, because in the year 1971, this problem of Boolean logic satisfiability, the SAT problem, was shown to be NP-complete. NP-complete problem has a certain meaning in theoretical computer science, but all that you have to understand is if a problem is NP-complete, currently we don't know of an efficient algorithm that can solve all the instances of a problem. What do I mean by an efficient algorithm? An efficient algorithm is one that takes polynomial time or even lesser time to solve the problem across arbitrary instances of the problem. SAT is still NP-complete, was shown to be the first NP-complete problem. So we don't know of a efficient algorithm to solve all instances of the problem. One algorithm that we saw, which was based on writing truth tables, is worst case deterministic exponential time algorithm. So if it's an exponential time algorithm, it's far from being polynomial time on the size of the input. But the nice thing is, even though the problem is NP-complete, for the past couple of decades, researchers have developed several techniques which we call as heuristics that can solve specific kinds of instances, special instances of the SAT problem for large formulas. Large, how large? Those formulas can have atomic propositions that can run into tens of thousands. It can contain 1 million symbols. Of course, specifically for software testing, we don't need these tens of thousands of atomic propositions and million symbols, but there are other applications of the satisfiability problem where these bag of heuristics help a lot. The tools that have been used to implement these heuristics are called SAT solvers. Solver because it solves the given formula and gives you an assignment of true-false value that makes the formula true, that satisfies the formula. So these instances, these tools are called SAT solvers. There are a few well-known techniques that they implement, and some of these techniques can in fact show that a formula is not satisfiable at all. It will show that it is unsatisfiable. We might need them in computer science for several different reasons. Now this is for propositional logic, which only had Boolean variables. What is the kind of logic we are using in testing? We are using predicate logic, which has several other different variables. So what is the difference between propositional and predicate logic? To reiterate the difference between propositional and predicate logic, propositional logic deals with Boolean variables or atomic proposition. It's used in programs, but the logic that we use for decision making in programs is predicate logic or first order logic, of course without quantifiers, as I've told you several times. What does predicate logic have? The and, or, not implies if and only if operators. The logical operators are the same. They are the same in all the logics. But now Boolean variables could exist as in propositional logic. Along with that, you could have other expressions involving variables of all other types. Strings, floating point numbers, integers. You could have constants. You could have functions, as I told you. You could have relational operators. All these don't exist in propositional logic, but they come into existence for predicate logic. The kind of predicate logic that we deal with is like first order logic, and it is known that the problem of checking satisfiability, that is given a formula which typically occurs as a predicate in a decision statement, can I check if there is an assignment of values to the variables that will make the formula true? That is the problem of checking satisfiability. This problem has been shown to be undecidable. By undecidable, what I mean is that I cannot come up with an algorithm that for all instances of the problem, of satisfiability problem for predicate logic, will take that instance as input, take the predicate as input, and give me one set of values or even a decision about whether the predicate is true or false. But like in propositional logic, here again, there are several specific instances of predicate logic that are decidable. In fact, one such instance is Pressburger arithmetic. Like for suppose I have the only function that I have is addition, and I'm considering inequalities as my relation, less than or equal to. I work with integers, and the only function that I deal with is linear arithmetic, which is addition. I allow subtraction also. Then this fragment of predicate logic is decidable. So people have come up with solvers or algorithms that can be implemented as solvers, which will compute whether a given formula is satisfiable or not. If we work with predicate logic, then the corresponding problem of checking satisfiability is called the SMT problem. SMT is abbreviation or short form for satisfiability modulo theory. So it's a problem of determining whether a given predicate logic formula, that is a given predicate which comes as a label of a decision statement, is satisfiable or not. That is there at least one assignment of values of the variables, functions, relations that come in the predicate that make the predicate evaluate to true. As I told you, predicates involve all these variables, right? They also involve functions and stuff like that. So because they involve all these kinds of variables, the resulting predicate or the logical expression corresponding to the predicate is usually interpreted, that is assigned a meaning within a certain kind of theory. Like just a little while ago I told you, right? Suppose you had a special case where you had only integer variables and only linear arithmetic on integer variables with inequalities, then that theory is decidable. But then this is a specific fragment. So that's why we use the word modulo. I'm checking for satisfiability. The full problem in its generality is undecidable, but specific instances and specific theories are decidable. So we call it satisfiability modulo theory. Like we saw for SAT solvers, there are SMT solvers, satisfiability modulo theory solvers, which are basically tools that work towards solving the SMT problem for a simpler subset of the general predicate logic. That simpler subset is of a lot of use in practical everyday life, like in software testing. So it serves a purpose. How are SMT solvers designed? There is a large bag of theory. In fact, there is an annual competition on SAT solvers that runs. In India, we have a specific school that runs on SAT and SMT solvers almost every winter. So they have a bag of algorithms that involve excellent algorithms from computer science. And the basic idea is that they are designed with a SAT solver as an underlying verification engine. So they basically reason about the given predicate logic at a certain level of abstraction by converting or transforming it into a problem for which you can use a SAT solver to decide. And this conversion has to be fast enough because SAT solver is itself a hard problem. And it's fast enough so that I can develop a tool over it and it can solve larger predicates. I won't go into the details of these algorithms, but if any of you are interested, there is plenty of material available in terms of online lectures that you could refer to. There are several different SMT solvers available and many of them are open source. So SMT solvers are used extensively in formal verification, program analysis, correctness of programs, several areas, automated reasoning. We use SMT solvers in this course for logic-based testing. Our simple goal is if you have a predicate that you've gotten from your code, after solving for reachability, after solving for internal variables, can you obtain test inputs for those test requirements on that predicate automatically? Yes, you can. We will use an SMT solver if the predicate is too large to do it by hand. We will also learn two other techniques right in the next week for testing. They are what we call symbolic execution and concolic testing, which are very closely related to what we did in terms of logic-based testing, and it will help us to solve and appreciate several problems that we've left open in logic-based testing. So this is the use of SMT solvers for us. So before I wind down, I would like to show you the Wikipedia page on these satisfiability modulo theories. So this is a nicely written page. Apart from giving an overview of what the theory is, what are the algorithms that exist, it also gives you a very big table that contains SMT solvers, which are the tools that we're going to use as testers to be able to automatically generate test cases. Based on your requirement, based on your operating system, based on the programming language support, the APIs that you have, each kind of solver exists, and some of them are open source, some of them are proprietary, many of them are open source. The particular solver that I would like to focus your attention on comes right at the end of this table. It's called the Z3 theorem prover. It is a solver that is being developed by Microsoft Research, circulatable under MIT license, and it's available for several different operating systems. It works for C++, C, .NET, OCaml, Python, Java, Haskell, and it supports all these theories. And the source code of Z3 can be found from GitHub. I encourage you to go and look at the page. This is if you're interested in understanding what Z3 is all about. You can experiment with that solver by giving it simple logical expressions. Try giving it x less than 3 and y is greater than 4, and where x and y are of type integers, and ask Z3 to solve it for you. Z3 will say yes, it is solvable, and here are values for x and y that make this predicate true. You could also try giving something like an array of integers to Z3 and ask if there is an assignment that makes the fifth entry in the array greater than 5. Z3 should be able to solve it and give you a satisfying assignment, or say that it is unable to solve a particular problem. So in testing, we will pick up a suitable SMT solver, say Z3 for now, and if we need to use it for generating test cases to satisfy test requirements, we'll pick up that solver and use it as a black box. We don't really worry about how the solver finds the test values, the satisfying values. For us, it's a black box, and we're going to use it as it is to obtain test cases. So this was a short module. I'll stop here for now, and I'll see you next week for symbolic testing, where we will continue to see logic-based testing, but from a different point of view. Thank you.